Hello everyone, I'm Nika from TAFU, founder and co-chair of TAFU, which is a nature conservation organization calling everyone to feel a sense of responsibility towards nature and humanity. You can see more about us on our website. We've been away for a while, but now we're back into our talks and interviews. How are we back? We're back with a special guest from one of my favorite fields, geology. Geology has always provided us with the resources we need and all the technology and solutions to achieve net zero, and even those we haven't yet defined, are deeply connected to geology. I'm delighted to introduce Dr. Colin Summerhayes, a distinguished geologist and oceanographer whose tireless work has significantly advanced our understanding of climate change and its far-reaching impacts. Dr. Summerhayes' career is a testament to his unwavering commitment to scientific excellence and the urgent fight against environmental degradation. Dr. Summerhayes began his journey with degrees in geology from Imperial College London and marine geology from Victoria University. He has held esteemed positions such as the Executive Director of UNESCO's Global Ocean Observing System and the UK's Institute of Oceanographic Sciences. And he's also chaired the review of the progress of International Arctic Science Committee. His extensive fieldwork in the Arctic and Antarctic has highlighted the critical role of polar ice in regulating our planet's climate. Also renowned for his exploration of the concept of Earth's refrigerator, Dr. Summerhayes has shown how the melting of polar ice exacerbates global warming. His latest publication, The Icy Planet: Saving Earth's Refrigerator, argues that achieving net zero emissions is not sufficient. We must also strive for negative emissions to truly mitigate the climate change and the challenge the world is facing. I'm also proud to announce that the University of Bedfordshire in Luton, in collaboration with TAFU, will host a public lecture by Dr. Summerhayes somewhere between mid-September and mid-October. The date is not yet confirmed, so stay tuned and keep checking our website. So, ladies and gentlemen, please join me in welcoming Dr. Summerhayes. I'll pass it over to you now.
Yeah, thank you very much. So maybe I could start with the share screen thing right away and get into the presentation. Okay, here we go. Right, so what I'm going to talk about for about half an hour is this topic of melting ice and rising seas, which is related to global warming. And it's important because it affects our children's and our grandchildren's future, and our future as well. So in a sense, you could think of this as sort of risk management for your children's world or your grandkids' world or whatever it might be. And anyway, there's big changes coming and we have to be prepared for it. This is the front cover of my most recent book, published in 2023, The Icy Planet, which is about the role of ice in the climate system. And down at the bottom, you see my current affiliation, which is with Cambridge University's Scott Polar Research Institute. So I wanted to start with a reality check, and that is that it's not all doom and gloom. And if you really want to follow this up, then I recommend this picture here is the front cover of a book published late last year by a woman called Hannah Ritchie, who is from Oxford University. And she's in charge of something called Our World in Data, which you can Google, and it contains statistics about all sorts of things going on in the world. In particular, she was interested in what we are currently doing to counteract global warming for the long term. And the positive message right at the bottom of the page there on the front cover of her book is how we can be the first generation to build a sustainable planet, which is very encouraging message. But let's start looking at the potential for climate damage. Where is the global temperature going? And this picture here comes from a guy called Jim Hansen, who's at Columbia University and used to be the director of a NASA organization collecting data on climate change. So what you see is a graph going from 1950 to 2050 along the bottom. And all the little black dots are the annual average temperatures. And you see them going up and down. The blue line just connects all of the dots. And what you can see is that these temperatures are gradually increasing with time. The red line is the average running through these, and I put a ruler line through this. That's the green line. You can see it was pretty straight from 1970 right up to about 2012. And then you can see that the ruler line continues as the green dash line. But what Hansen has realized from these most recent data that I'm circling there with my cursor, since about 2013, we've had these very significant departures from this sort of dash line. And the purples, pinkish purple color are the projections for the El Nino of late 2023, early 2024, and the projected following La Nina events. So these are variations in the Pacific Ocean that give us warmth and followed by cooling, warmth followed by cooling, and so on. You can see two of these back here. There was one in 1997-98 called a Super El Nino, and there was another one in 2016. And it looks like the one for the end of 2023, beginning of 2024 is going to be another Super El Nino. So his thesis is that we're no longer following the dash line. We are following this yellow projected line into the future, which will take us into some warm territory. So the rate of global warming is accelerating with time. These figures down the left-hand side are the temperature anomalies. So you take the average for a certain period. In this case, the average relative is for the period of 1880 to 1920, and then what you do is calculate the difference from that average. So that's what this curve means. Now, the UN has a body called the UN Framework Convention on Climate Change, and these guys meet. Includes our politicians and climate scientists, and they meet every year in November. They met recently in Glasgow in 2016, but they've met in other places since then. And what they've agreed as a sort of global agreement is that ideally we'd like to keep this rise in temperature that you see here to no more than 1.5. So there's 1.5, and you can sort of draw an imaginary line across there. And as you can see from those sort of purpley pink colors, we're already right close to that. And that would be their lowest guardrail, and then their upper guardrail is 2 degrees centigrade, and you can see where the 2 degrees centigrade line would be if you read off 2 degrees on the left-hand scale and just project it across. We're going to get there by, well, about 2040, 2050. And they regard that as too far, and they really don't want our global average temperature to go beyond that. So the question is, how do we humans adapt what we're doing so that our temperature doesn't increase by another half a degree, so that it goes over the 2 degree line? That's what all this is basically about. And for those of you who wonder, is it here too in the UK? Yes, it is. We have something called the Central England Temperature Database, and it dates back to 1659. And these are the data. You can see on this graph at the bottom are the dates. So the left-hand date is 1660, and the right-hand date is 2020, and it's gone on beyond that too. And the average, which is the line across the middle, is the 1961 to 1990 average. So what you see here is that back in 1660, 1690 down there, and all through most of their following period, right up to about 1930 here. The predominant color is blue, which means the temperatures were below the average. In fact, as you see back in 1690, they were well below the average. This is a period called the Little Ice Age, when the Thames actually froze over. But what we've seen since 1930 is lots of this pink stuff above the line, especially since about 1970, when you see this big increase. And if you read across to the left, you see that reaches 1 degree centigrade. So even in the UK, for the past, well, since the year 2000, our temperatures have been really up in the 1 degree above the average. So it turns out that we had our UK heat wave record in July 2022. Our hottest June was in 2023. The world's hottest day was in July 2023. And temperatures in 2024 have just gone on getting higher. In fact, the March and April temperatures globally were higher than the ones that we saw on that previous graph. So let's go to the next one. Okay, so 2023 turns out to have been the world's warmest year, and we got lots of wet, lots of rainfall. So England and Wales had the warmest February on record, but also lots of flooding. And the reason for that is that if you warm the air, it can hold much more moisture. So warming the air by 1 degree, you get 7% more water in the atmosphere. So you get more rain in places where it normally rains. And also, if you look at the graph on the right, it goes from about 1965 up to 2023. And what it shows is lots of wiggling up and down, but the dashed line shows you this is the number of ground frost days per winter for the UK. So we've been getting much warmer winters, and so we're getting a lot less frost, which is nice. March 24, as it says in the bottom, was the warmest March yet globally. So lots of things are going on, and the most recent data is really intriguing because it shows, as you see here, that the oceans are unusually warm. This comes from the BBC, which is reporting sources from European Centre for Medium Range Weather Forecasting, and these are temperatures measured between 60 north and 60 south. So what you see here, there's the temperatures going up the left-hand side, and along the bottom you've got January, February, March, etc., right through to December. And all of the grey lines represent the years between 1979 and 2022. So let's look at 2023. So it starts out at the top of what we previously saw with these grey lines, and then it starts to diverge around about April. And we get this really significant divergence from all those previous measurements with a margin of almost half a degree by the time we got to August. And that margin has continued right through 2023. And then we get to 2024, which is the year we're now in, of course. And what you see there is that the temperatures were a good half degree warmer, and they've continued to be warm. They're even warmer by a significant amount compared with 2023. So these are record-breaking ocean temperatures. And the picture on the right shows you globally where the warmth is focused. And you can see there's a lot of warming in the Pacific Ocean. That's probably due to the El Nino, which is a Pacific oscillation. But we also see tremendous warming all through the Atlantic, which is kind of a surprise, and also significant warming down through the Indian Ocean. You can also see significant warming up to the top left of there, coming around to the top right. That's the warming in the North Pacific, which goes right across to Japan, China, and Korea.
Oh, wow.
So lots of things going on. Not all the world's ocean warming at exactly the same rate, but you can see from the colors on the legend that there's almost nothing down in the blue colors. So really warm ocean, and this is a kind of a worry for people interested in the biology of the ocean. Um, One of the reasons that the ocean gets so warm is that actually, you may or may not know this, but 90% of the heat of global warming is actually not in the air, it's in the ocean. So where is all this coming from? Well, it's coming from our emissions, and particularly carbon dioxide. And so what you see here in the top left is a graph going from 1850 right up to nearly the present, showing the way we've been burning fossil fuels. So the orangey color is coal. And so, during the Industrial Revolution and back in the 1850s, we were generating slightly increasing amounts of coal as our populations grew. And the red line is 1950. So you see, after 1950, that the coal burning underwent a really significant increase. And also you can see here to the left of the red line that we started burning oil, for example, around about 1900, very thin amount of green line there, and you follow that. I mean, it gets sort of thicker as we get up to World War II, but surprisingly, not an enormous amount. You see, after World War II, after 1950, goodness me, this huge increase in the amount of oil burning. And similarly, you look at natural gas, which is the purpley blue color, and you can see not much used at all before 1950, and then from 1950 onwards, you see how that starts to ramp up as well. So we have really hugely ramped up our fossil fuel burning since 1950. And that's why when you look at these various graphs of temperature, you see that they really start shooting up after 1950. And it turns out if you add all this fossil fuel burning bits together, it turns out that more than 90% of all the fossil fuel we've ever used has been burned since 1950. So, it's a fairly recent fairly recent problem. My mother and father and my grandparents, lived back in this earlier era. The climate was completely different. Almost nobody was burning much fossil fuel. You can see on the right-hand side, there's another graph here. This is the emissions of methane. Methane is another important greenhouse gas. And you can see going back to 1850 again, it's a very slow increase. And then it starts to really steepen around about 1950, just like the one on the left. And it's still very high. We're still putting lots of methane into the air. And much of that comes from what you may have heard of as fracking. That's where you pump water down into shales to break them apart, to release the gas that's sort of locked in the shale. And that gas then comes up to the surface very slowly. It's not like a gusher that you might have seen in old-fashioned films of the oil business. But the problem is that the wellhead facilities and the pipelines into which the methane goes leak, and so that puts it into the atmosphere, and it's a stronger greenhouse gas than even carbon dioxide. Down the little box in the bottom corner, this is the excuse me, the cumulative excuse me, the cumulative emissions over the past 200 years, well, since 1751. So what it tells us is in tons of carbon per person, who has burned the most fossil fuel. And clearly the winner is the blue on the left. That's the United States. UK comes second. Yeah, we get the silver medal. We're in the middle. That's that pink thing. Germany comes third. They get the bronze medal. And then the other countries, see mostly Western industrial countries, Canada, Australia. There's the rest of Europe, Japan, obviously, and Russia. So all of us together, the main industrial OECD countries, have contributed most to this problem. When you look at China, you see, people talk a lot about China. Wow, they're burning all that coal. This is disastrous. China's overall commitment in the past 200-year period is minuscule, and so is that from India, although undoubtedly they will grow as we go into the future. So we know, who caused the problem. It's not about guilt, though. It's about, okay, what do we do now? So what we want to know is how unusual is what we have now compared to what went on in the past? So the way we find that out is by drilling cores into the Antarctic ice. And on the right, you see a hand, a thumb, and a forefinger holding the end of an ice core. So when we drill down, we use a drill bit, which has got a hole in the middle. And what that enables us to do is to extract a solid rod of ice from down into Antarctica or Greenland, or wherever it might be.
Oh, wow.
Now, it turns out you'll probably know when you walk on snow, you hear a crunching noise, and that crunching noise is the expelling of air, because when snow falls very slowly, it traps pockets of air. And then gradually, as more and more snowfall comes onto the older snow, that snow gets compressed. And so the pockets of air get smaller and smaller and smaller as you get more and more snow. And eventually, when the snow turns to ice, those little pockets of air turned into bubbles. So all these funny little nodular looking things in that slice of the ice core, he's holding it up to the light, so the light's shining through it. They're pockets of, they're bubbles of fossil air. Can you believe that? It's just amazing. Most geologists are amazing when I tell them that you can find fossil air. So let's look at the fossil air concentrations of carbon dioxide. So the graph on the left, we're going from the year 2000 on the right back to the year 1000 on the left. And on the left-hand scale, we're looking at carbon dioxide concentrations from 260 to 400 parts per million. And so what we see is for most of this period, in a whole range of different Antarctic ice cores represented by the different symbols there was 280 parts per million for the whole of that period. So quite low. And then from 1769, which is that thin gray line that you see going up the right-hand side, you see the carbon dioxide starts to increase slowly at first, then steepening amounts in the ice cores. And then what we see in the ice cores maps onto the blue line, which is what we've been measuring in the air since 1957. So that's modern CO2 in the atmosphere. So it turns out that what we humans are doing is increasing carbon dioxide in the air by 20 parts per million in about a decade. Whereas in nature, what the ice cores tell us is that in nature, it was increasing 20 parts per million in 1,000 years. So we're doing this 100 times faster than nature. Now, this graph was put together by David Mackay in 2009. And if you want to read his book, Sustainable Energy Without the Hot Air, it's a very good read. But at the time he drew that graph, the carbon dioxide level at the top of the blue line was actually just below the 400 parts per million CO2, whereas now we're up at 425. So we are really increasing this, ramping it up. There's a further problem, though. This is just a graph of carbon dioxide, and it's not the only greenhouse gas. I showed you the methane figure, for example. If you add all of these greenhouse gases together, ignoring water vapor, we are currently at 423 parts per million of carbon, what they call carbon dioxide equivalent. You take all these different greenhouse gases and you calculate what they would be if you converted them into carbon dioxide. So this is quite a significant amount because it's over 3 million years since the planet was at a level where there were 523 parts per million of any greenhouse gas in the atmosphere. So this is a significant problem. So what's happening? Well, we are melting the ice and losing our refrigerator. So let's look at Antarctica on the left. The colors represent the altitude. So you've got a line down the middle. Actually, that line down the middle, where it says 0 at the top, is the Greenwich Meridian. So this is due south of us. And on the right-hand side, that's the east, it's quite high. The red and yellow colors take us up to 3,000 meters. In fact, the peak height is around about 4,000 meters. On the left-hand side, Antarctica is much lower. The blue colors, pale blue colors, this is the altitude. In fact, there's a scale bar down at the very bottom there that shows you on the right hand, the top red is getting up to over 3,000, and the bottom, excuse me, I just knocked the wrong button there. So the blue colors are going down to sea level. So if you melted all the ice on the right-hand side, your sea level would go up by 55 meters. And that has happened in the past. Let's see, about 50 million years ago, the overall sea level on the planet was about 65 meters. And that's because added to that, we would have had the ice on the west, in West Antarctica. There's 5 meters worth of sea level rise there. And in the lower graph, you see Greenland to the same scale. And Greenland has the equivalent of 7 meters of ice. So add those together and you get 12, you get 67 meters. And we've been there before, you know, geologists know that. So what's happening now? Well, if we look at the right-hand side, you can see what's been happening since 1992. The scale at the bottom, the times go from 1992 up to 2021. So the blue color is Greenland. So we imagine that there was zero change in 1992, and then we see that follow the blue line, which you can just about see in there, and there was just a slight diminution of Greenland's ice up to about 2002. And then the rate started to really increase significantly, and it got progressively steeper down here. And so altogether, if you add up, if you look at the left-hand scale, that goes down to minus 5,000. Now the 5,000 is gigatons, and a gigaton is a billion tons. I've got no idea how many African elephants that would be, but probably more elephants than there are in Africa. And then we look at Antarctica, which is the purple line. So again, you see not much change from 1992, sort of flattish. And then it too, around about 2002, it starts to increase slowly. And then the rate of increase steepens. And suddenly we get down to about here. And if you read off to the left, that's about 2,500 gigatons. So between them, the melting of Greenland and Antarctica has put that represents 7,500 gigatons of ice lost from land and poured into the ocean, which helps to raise sea level. That's not the only thing that makes sea level go up. The other thing is that when you heat water, it expands. So global warming warms the ocean expands, sea level goes up, And then in addition, you melt the ice turns to water, and the water goes into the ocean, and it goes up further. So what's been happening here? We've got a graph that comes from the World Meteorological Organization, which monitors this stuff. This is 2022. And we start on the left in 1993, and the sea level is in millimeters. So we see that the black line is a sort of wiggly rise in sea level. And I put my ruler through that. That's the purpley line. And you can see from that there wasn't much change, much acceleration in sea level rise during that whole period, right up to about 2010, 2010. It was about 2.1 millimeters per year in the earlier period and 2.9 in the latter part. And then you see we get this real divergence from about 2010 onwards, and we get a steepening. So that goes along with that rise that we saw in the carbon dioxide and the rise that we've seen in the temperature. Everything is accelerating, and we're now at a rate of 4.4 millimeters per year, and that is likely to get steeper. In fact, the projection for the year 2100 is for a rise of about 2 meters. Just imagine what that will do to all the nice places and beaches that you like to go to on holiday. Okay, so that's going to be a problem for coastal megacities. Now, you may or may not know, but I mean, it's pretty obvious when you look at a map that most of the big cities of the world are actually located on the coast. Even places like Chicago are on the coast, except it's a coastal lake. So we've had to protect our cities, and we will have to protect them in future. This is the Thames Barrier. You might have seen the Thames Barrier, and it was built not because of sea level rise. It was built because the North Sea is shaped like a funnel, like that. Okay, and in 1952, a big storm came down the North Sea. The wind was blowing straight down into the funnel, and it was pushing the water in front of it. And that flooded London, and it flooded lots of the Norfolk coast and the Essex coast. It killed, and also the Dutch coast. It killed about 4,000 people. And so, amongst other things, lots of coast defenses were put in, and the Thames Barrier was built to withstand a possible storm surge of as much as 2 meters. Okay, well, now we know that that's not enough, because we're projecting that the sea level rise by the end of the century will be another 2 meters. So they will have to completely redesign and rebuild the Thames Barrier to withstand that sort of rise. The sea level may go on rising beyond that. I mean, that's looking further into the future, but this little graph on the right comes from the Environment Agency and from its Science Media Centre. And what it shows is the parts of the UK that would be flooded extensively by a rise in sea level of 7 meters. Now, you might think, yeah, that's a bit extreme. But on the other hand, we do know that back at the previous warm period, about 120,000 years ago, the sea level actually was already up at about 15 meters above present levels. And we know from geological records that there have been plenty of times in the past when that's also been the case over the past 3 million years or so. So it's not so far-fetched, at least not in geologists' minds. And the estimated bill for a flood of London would be at least 30 billion, which represents 2% of GDP. So in a way, although Antarctica is a long way away, it doesn't really matter where you live. If you're on a coast somewhere, all this global warming and ice melt is going to affect you. So what do we do? Well, here's these guys I call the three wise men. Their focus is on how to live sustainably on Earth. And David Attenborough, interesting character. We all know him for his wildlife films, but up until about 10 years ago, he didn't believe in global warming. But he gradually became convinced by the growing mass of data that the warming as it was happening was not doing nice things to the wildlife that he liked to go out and photograph. So he's become a convert. Mark Carney, you may know of as the Canadian director of the Bank of England. And for the meeting I told you about, the UN Framework Convention on Climate Change meeting in Glasgow in 2016, he produced this book. It was about values. He's an economist, But what he was interested in was the fact that in our economic system, as it currently works, has no value on the environment. Economists regard the environment as what they call an externality, and externalities don't have any value. And so, what it means basically is the economists haven't got a hope in hell of understanding what climate change is doing to the environment and what that will do to money. Uh, so go tell that to your friendly local economist. And here on the right is Bill Gates. Bill Gates, I'm sure everybody knows who Bill Gates is, but what they may not know is he's a technophile. He loves technology. And so what he's done is looked into all of the technologies we currently have available right now to be able to do something about global warming, how to bring the carbon dioxide down so we don't get overly warm. And his view is that we have all the technologies we need. We just need to apply these. We do need some breakthroughs. So he's listed all these things. It's all there. Any politician anywhere in the world can read this stuff. Whether they do anything about it is, of course, a different question. But you can get a hold of these things. You can buy them in Waterstones. You can educate yourself and your family and friends and tell them all about it. So going back to our early diagram, let's just have a quick look at that again. There's that warming. There's the acceleration in the warming represented by the yellow. And what governments are talking about in order to keep the warming within this 1.5 to 2 degrees centigrade level between these two guardrails is that we have to adopt a policy called net zero. And what this means is that you can carry on burning fossil fuels, you can carry on putting carbon dioxide into the atmosphere, but you must take out the same amount that you put in. So essentially what that means is you maintaining carbon dioxide at more or less its current level, or something slightly above it, our current level. Now, they obviously haven't talked to any scientists about that, because if you maintain carbon dioxide at somewhere near its current level, and if you take all of the gases that we talked about, carbon dioxide, methane, and the other greenhouse gases, remember I said it was 523 parts per million. That is larger than the amount of carbon dioxide in the atmosphere during Pliocene times 3 million years ago, when sea level was an awful lot higher and the climate was an awful lot warmer. So maintaining carbon dioxide will melt the ice, remove our refrigerator, and help to keep the planet warm. So net zero is really a political concept that doesn't actually have much meaning when we think about science. To get down to 1.5 degrees, which is the lowest of the UN guardrails, we will have to have what people call negative emissions. Now, what that means is you have to take out more carbon dioxide than you're putting in. So you're going below the level of net zero. So we need to do an awful lot of thinking about that and an awful lot of influencing of our political masters. What are we doing in the UK? Well, the graph on the left is an interesting one, because what it shows is where all our electricity is coming from. And the bottom timing goes from 1996 to 2019. Renewables are in orange, and you see that they've been increasing rapidly only since about 2006. But they have increased an awful lot, to the point where about 50% of our electricity comes from solar and wind, which is a good thing. In the middle is the map of the UK. All the red dots are onshore wind farms. All the offshore little blue squares are offshore wind farms. So that's where all this is coming from. But on the right is the map showing which areas the government's going to license for really major wind farm developments in the future. In fact, this one here is the Dogger Bank. And the Dogger Bank is a major fishing ground, but they've already started putting in wind turbines there. So we will see these other areas fill up with wind farms, which will increase the renewable energy that we get by a large factor. So moving on, what can we do? Well, what we've looked at there is what governments could do. There are lots of other things governments could do. What can industry do? Well, obviously industry can do a lot, but industry doesn't usually do a lot if there's no profit. So industry will do things if governments regulate industry so that it does, what's required. But we individuals can also do things. We can insulate our houses better. The UK housing stock is mostly ancient, so most houses are not well insulated. We can add solar panels to our roofs. It used to be that these cost a bomb, and the payback time was about 15 to 20 years. But now the costs have really dropped. The more of these you manufacture, the lower the costs. So solar panels are now really quite cheap. And the payback time is now around about 7 to 8 years, not 15. So it's really worth having them. Fitting a heat pump is important. They will keep your home warmer in the winter and cooler in the summer. You can get away from petrol or diesel vehicles to hybrids or an electric vehicle. In the future, we may be moving towards internal combustion vehicles driven by hydrogen, which is a high density fuel. We can obviously plant more trees and hedges because trees eat carbon, basically. But what's most important is we have to tell government what we want. That, our votes are very important. And if you can't do it by yourself, you feel you're too small, or your voice is not being heard, then you can use another intermediary like the Friends of the Earth or WWF or the Council for the Preservation of Rural England. There are lots of these non-governmental organizations that will take your message to government. In fact, the Friends of the Earth have recently sued the government over the weakness of its climate change strategy, and they've won twice. So you can talk to your friends, family, and colleagues, and so on. And when you have children, you can obviously educate them, or you can go into a school and talk to kids. It's their future. So back to the final one. It isn't all gloom and doom. It might sound it from my presentation, but what I'm talking about is where we are now and where we're going now. And what you have to think about is all the changes that are coming in the future. Students at places like Imperial College, engineering students, they're all keen to make the next big breakthrough in getting our renewables to be cheaper and so on.
Mm.
So it isn't the end of the world, but we do have to get those technologies. We have to apply those technologies, and that's what we really need to do. So there, I'll end it with one of my Antarctic slides and open it for questions if you have any.
Yeah, definitely. Quite a few, really, I'd say. Um, I have a few about the presentation, but before we go there, can I ask you a bit about yourself, actually? Could you tell us a bit about your journey into geology and climate science and what inspired you to focus on these two fields, as well as oceanography?
Yeah, well, I started out, I did physics, chemistry, and maths at A level. And I was told that, my probable future would be working as a chemist in ICI. And I thought, no, that's not really what I want to do with my life. I like the outdoors. And I looked around and I found one of my great interests was geography. And so I learned a lot about geology through geography in school. And they didn't teach geology in my school. In fact, teaching of geology in schools is really minuscule across the country.
Mm, yeah.
So yeah, I had to find out about stuff, and I figured geology sounded really interesting. You get out in the field and see the world. So I did that, and then when I got into geology, uh, I went through University College London and then Oxford. I found that the interesting part was geochemistry. They're using chemistry to solve geological problems. So my PhD at Imperial was actually in geochemistry,
Oh,
and yeah, and the thing that really began to interest me was the fact that 72% of the surface of the Earth is actually the ocean. And
mhm.
we just didn't know much about the ocean. What was under the ocean? We knew a lot more at the surface of the moon than we did about the ocean and what was underneath it. So I became very interested in oceanography. as a sort of study field where you could start looking at the way the atmosphere interacts with the ocean, the way the ocean interacts with the chemistry, the way the chemistry interacted with the biology, and how all of that led to the sediment record. And when you looked at the sediment record, then you could backtrack through it to get it past climate change. I thought it was utterly fascinating that you had a window into past climate through geology, particularly through the sediments on the seabed. So that's how I got into this stuff.
That's really interesting. How exactly do you mean that you can see the past climate through the sediments?
Okay. Um, you have plankton. You know what plankton are.
Mhm.
So there's two kinds of plankton. There's the plant plankton, and the plant plankton is fed on by the animal plankton. So there's phytoplankton is the plant plankton, and zooplankton is the stuff that eats that. And then the fish, of course, eat the phytoplankton. So I'm not really interested so much in the fish. But the plankton grow in the water, and in the water you have oxygen and carbon, and nitrogen, which they use to build their bodies. And it turns out that oxygen has two major isotopes: oxygen 16, which is light, and oxygen 18, which is heavy.
Mhm.
So if you a Nobel chemist guy called Harold Urey in Chicago University discovered this back in the early 1950s. If you evaporate water, the the oxygen that evaporates, the water that evaporates first is H2O with oxygen 16 in it, the lighter of the two isotopes. And that leaves the ocean enriched in the other oxygen isotope, which is oxygen 18. So you get this differentiation going on. And so when the plankton are growing in the water, if the water is very warm, their bodies will contain carbon dioxide in which the oxygen has more of the oxygen 18 because that's the indicator of a warmer ocean. Okay, so you can then take a sediment core, you drill, you get your core of sediment, and
Mhm.
you analyze the little tiny layers, which are, the annual accumulations, and you find out how that ratio of oxygen 16 to 18 has changed with time. And what it tells you, it within the skeletons of the particular organisms, the zooplankton, we call these little zooplankton foraminifera. Okay, so you look at the forams and
Mhm.
analyze the ratios in a mass spectrometer, and bingo, you have a temperature record. It also happens that the phytoplankton species themselves change with temperature. Okay, so the species, the ecology is changing, and so
Mhm.
you have these two things. There's the nature of the phytoplankton and the nature of the zooplankton changing with time down the core, and at the same time, the oxygen 16-18 ratios are changing down the core. So you have these two things working together to give you it's like a thermometer, of past climate change. The other thing that came up, so we've known that for a long time, since 1950s.
Oh well.
But more recently, we've started doing these big, long drill cores into the Greenland and Antarctic ice sheets.
Mm.
And when you do that, what you're getting is another kind of water. Okay, this time you have to imagine, okay, so during a warm period, you've evaporated water with the lighter isotope. So it's fallen onto Antarctica. Okay. And so whereas your plankton in the ocean has more of the heavy oxygen isotope, at the same time, your ice core has more of the lighter isotope, which evaporated out of the ocean. And so when you go down the ice cores, you get this same sort of ratio changing, but it's inverse to the one in the sediment cores, but tells you the same thing. It tells you the same story. It tells you the temperature change through time. It's just absolutely amazing. And so we now have sediment cores through the ocean that go back, several millions of years. And on the ice sheet, the longest core we have so far goes back 3,500 meters, and it gets us back 800,000 years. Just imagine drilling a solid rod of ice 3.5 kilometers long.
Pretty
Actually,
incredible.
yeah, but it comes up in sections 1 meter long at a time, and you then have to store them in a refrigerated place. There's lots of these ice cores stored at the headquarters of the British Antarctic Survey in Cambridge. So
Oh,
if you yeah, if you want to, you have to put clothes on to go into the core store because it's at -25.
oh dear.
Yeah. So
That's
we have these wonderful
incredible.
records. The ice cores go back as I said, 800,000 years. And currently, they're working in Antarctica to drill down to more than 1 million years. So that's the next target.
How deep would that be? Many years.
We're probably getting on for 4 kilometers.
Crazy.
Yeah, well, the mass of ice on Antarctica is huge. It gets up to, I think, the thickest ice, the top of the ice gets up to 4,900 meters, something like that.
Oh
Anyway,
wow.
the massive ice is so heavy, it sits on the land and depresses the land, which is the Antarctic continent, by 2 kilometers below sea level.
Oh wow.
Yeah. So if you took all the ice off, that land would slowly come up and it would come above sea level and you'd have a land mass there. In fact, 100 million years ago, in the middle of Cretaceous times, there was almost no ice at all on Antarctica. It was the continent was at the South Pole, but it had almost no ice on it. So, it was just a continent with dinosaurs and trees and ferns and what have you.
Wow.
Not a lot of people know that.
It's incredible. Okay. Oh dear. How do you say because you have that background in geology then and oceanography. So when went into climate change, how would you say that your background affected your view on climate change?
Well, what I learned from the geological record, I actually in 2020, I published a book on all of these changes. It's a textbook, Paleoclimatology, and it takes the climate back to 700 or 800 million years ago and
No.
looks at all the climate changes from there to the present. Um,
Mhm.
it's like I say, it's a textbook. It's probably a bit expensive for most students, but if you wanted to get one in your library, I'm sure it would be useful.
Oh,
Anyway, so uh, I got interested in past climate change and
mhm.
how you could measure past climate change back through the ages for millions and hundreds of millions of years. Um, and I just found it really exciting, to understand how the climate works. And the fact that in order to do that, you had to understand that you had to get away from the single discipline silo approach of modern science. So there's physics in one box, biology in another box, geology in a third box, and so on. That doesn't help you understand how the Earth works. Because as I said at the beginning, the wind blows on the ocean, that causes ocean currents. The ocean currents cause the upwelling of nutrients. The nutrients then feed the plankton. The plankton die, they sink to the bottom. All of these things are connected. That's what we're looking for is the interconnection. In fact, I had this book which I'll get out to show you. The way we're now approaching the Earth and what we call the Earth system, which is tying together all of these subsystems
Mm.
is through something called Earth System Science. And if you wanted to find out more about Earth System Science, can you read that? Or
Yeah, got it.
is it backwards?
No, it's right.
Right, okay. It's by a guy called Tim Lenton, who from the University of yeah,
Doesn't matter.
it's in Devon.
Uh,
Yes, yeah. Okay. Anyway, so Earth system science is what you need to be finding out about because that will tell you how the climate system is working, had worked in the past, is working now, and will continue to work in the future.
sounds really interesting. Make a note of that one too then. There was something I wanted to ask. Can I remember it now? maybe not. Gone. Triggered something and then it left. Okay. Something else I wanted to ask from before was you mentioned Earth's refrigerator. How exactly does that work? Because I know you mentioned that it's
Hmm.
what's it called? Polar ice and ice sheets, but how does that work?
Okay. Well, imagine the polar regions. It's very cold, so you've got lots of ice. The surface of the sea is frozen for most of the year. And what you may or may not know is what I haven't talked about is water vapor as a greenhouse gas, because water vapor is in a way is the major greenhouse gas because there's a lot more of it in the atmosphere than there is of carbon dioxide. Uh, but the water vapor is concentrated in the middle and equatorial latitudes. Um, where it's warmer, where you get more evaporation and you get more water vapor into the air. So the water vapor has a far greater effect than carbon dioxide in the middle latitudes and the tropics. But when you get north or south of those areas, under the extreme cold of the Antarctic or the Arctic, literally the water vapor is frozen out of the air. So the air contains very little water vapor. So it's not such a potent greenhouse gas. The main greenhouse gas that has an effect in the polar regions is carbon dioxide and the other greenhouse gases like methane and so on.
Hmm.
So what they do is they slightly warm the Arctic or the Antarctic. Let's talk about the Arctic. They slightly warm the Arctic,
Hmm.
and that's important, but it takes an awful lot of warming to actually melt the ice. In the meantime, what's going on is that the solar rays are coming in, hitting the ice, hitting the snow, and just being reflected back into space. And so, in a sense, they're not having a warming effect, they're just bouncing back into space. Um, so that acts as Earth's refrigerator, that reflection of the solar energy from the surface of the ice and snow.
Okay.
Uh, and so that is Earth's refrigerator. We have at both ends of the planet, we have this ice and snow reflecting solar energy away. And that contributes to what's called the Earth's albedo, which is a scientific term for its reflectivity.
Oh.
And it's good that we have that because it helps our climate to be
Hmm.
moderately warm. Okay, so then when you add global warming to this, what you are starting to get is the melting of the ice, and that means you're losing that ice and losing the snow, so you're getting less reflection. And instead, the solar rays that were being reflected are now coming straight into the ocean or into the Arctic land and warming the surface. And that warm surface is then reflecting infrared energy, heat, back into the atmosphere that adds to the global warming effect. So we don't really want to lose our refrigerator. um,
Yeah.
and if you do lose your refrigerator, obviously one thing that happens if you lose the ice, then your sea level goes up more. But it's that loss of the reflection that's really quite important.
Yeah,
So
well, it's like when you wear a white top, you don't get quite as hot as when you wear a black one, but
yes, that's
it's
it.
that extreme level.
Yeah.
Oh. So, you mentioned there was this, you mentioned the other geological time frame, time period that was when we had the same amount of parts per million as of carbon dioxide or similar. What was the climate like then? What would it what was the ecology like then? Was it similar at all, or was it extremely different?
Okay, well, let's go back. If we go back 3.5 million years, we're in what geologists call Pliocene time. And in Pliocene time, the planet was, on average, about 6 degrees warmer, and there was minimal ice and in the Arctic. In
Mhm.
fact, you had forests growing on Greenland, and next to Greenland there's a big island called Ellesmere Island. So it's very, it's
Oh,
something about 80 degrees north, so it's quite close to the pole. And and there were crocodiles there and other sort of creatures that you currently associate with the tropics. And so we know that conditions then were very, very different, and it was an awful lot warmer. Um, and at the time, there were, we think that from a whole variety of evidence, we also have, just as we have evidence for past uh, temperature change from the oxygen isotopes, we also have evidence about the past change in the carbon dioxide levels from a variety of sources. Let me see, the best example would be fossil leaves. If you look at a leaf, at the underside of a leaf, it's got little holes in it, which are called stomata. That's how the plant breathes. It sucks in carbon dioxide through these holes and it emits water vapor. And so the number of these little holes is proportional to the amount of carbon dioxide in the air. If there's less carbon dioxide, there are more holes because the plant needs to work harder to get the carbon dioxide in. If there's more carbon dioxide in the air, if there's less carbon dioxide, then you get more holes, and so it can suck more carbon dioxide in.
Wow.
So we can go back and get fossil leaves, and we can look at those fossil leaves, and they will give us information about the past carbon dioxide levels in the atmosphere. There's another thing about fossil leaves too. The people who study fossil leaves are palynologists, and they can tell from comparing leaf types from fossil localities with similar leaves living today that there have been changes in the temperature. So there are a variety of ways of getting back at this. So we
Wow.
can get both the carbon dioxide level and the temperature from eras like the Pliocene, and that confirms, there was something like 450 or even 500 parts per million of carbon dioxide in the atmosphere at the time when it was so warm that we had crocodiles and forests in the North Polar region.
Wow.
Sounds crazy. Sounds crazy, doesn't it?
Yeah, just a bit. Wow. It's also sort of crazy to think about how everything is so connected, like you said, with the CO2 and the stomata, plankton and the oxygen. It's just crazy, really. You think it's all linked, but it's amazing to see things that are linked to such an extent.
Yeah.
Wow. Um, One other thing I wanted to ask is, over the past decade or so, what would you say is like the most alarming trend that you've seen in polar ice? Like, and where has it been?
Hmm. Okay, the most alarming trend in polar ice has been the loss of Arctic sea ice, and to a certain extent also the loss of Antarctic sea ice. You have to remember Antarctica and the Arctic are very different polar regions.
No.
The Antarctic is very much colder than the Arctic for a whole variety of reasons. The main reason is that if you imagine your globe, if you have a globe there, the Antarctic continent is just surrounded by ocean, and the wind runs around Antarctica really quite strongly, and as it does, it pushes an ocean current, the Antarctic Circumpolar Current, and those two together act as a wall to keep the heat from the north away from the continent. Whereas if you imagine the Arctic is exactly the opposite. It's an ocean surrounded by land, and the warm air can get in from just about anywhere, and warm ocean water can get in, say, from the Atlantic up past the UK. We have a branch of the Gulf Stream coming up past the UK, up the Norwegian coast, and into the Arctic. So that means that the Arctic tends to be quite significantly warmer than the Antarctic. But let's talk about the sea ice because that's the main signal. This is a major environmental signal. What's happened since 1980 is that we have lost in summer half of the area of Antarctic sea ice. So in other words, there's a lot more ocean exposed, and that ocean is dark colored and it can be absorbing solar rays instead of reflecting them, which is what the ice would do if it was still there. And the other thing is that ice used to be back in 1980, much of that ice was up to 5 meters thick. So it was a really solid chunk of sea ice. Nowadays, most of that ice is 1 meter thick or less. And so it's there's very much less volume of ice, which means it will be increasingly easy to melt it all away as we go into the future. So this is like a sort of what scientists call a tipping point, where you start warming something and it gradually warms and warms and warms, and suddenly it all goes, bingo, just like that.
Mm.
And that's the kind of thing that we would expect happening. The prediction is that from climate models and so on, that we may have lost most of the Arctic sea ice in the next 25 years.
Wow.
Right now in summer, there's only 4 million square kilometers where there used to be 8 million. And so, because that remaining 4 million is a heck of a lot thinner than it used to be, it could go fairly quickly.
Wow.
That's a major environmental change on the face of the planet. In Antarctica, there's much more sea ice because, as I explained, it's a much colder place. But even there, the sea ice began decreasing quite significantly around about 2015. Up until that time, it hadn't shown much change, but now is showing much more change.
Wow. That's wow. That's very significant. Is Yeah, I know you mentioned negative emissions a lot, and what's it called? Is that one of the reasons, as well as the what's it called, the parts per million being quite high?
The emissions?
Yeah, you said negative emissions, that we have to aim for negative emissions, and
Oh
is
yes, yes,
that one
negative
of the
emissions. Yeah,
reasons?
yeah. Well, if we right now, if you imagine we've got carbon dioxide level up here, and what we really want is for that carbon dioxide level to be down here somewhere, right?
Hmm.
So to do that, you've got to pull carbon dioxide out of the air, and there are ways to do that. There's a guy in the States working on gigantic fans which suck air in and blast the air over a catalyst that will actually help to absorb the carbon dioxide out of the atmosphere. Or they pass it through a liquid which will take the carbon dioxide out. So we know it can be done. It's been done in the laboratory, but it probably would be rather expensive to do. So, nobody's all that keen on doing things that are extremely expensive for, for obvious reasons. There
Mm.
are other ways of doing it. There's a guy at the University of Sheffield who is working on the fact that if you take uh, silicate crystals called olivines, which are very common in certain dark colored rocks like basalt. Okay,
Mm.
you
Yeah.
take you grind them up and put them on farm fields, and they will absorb carbon dioxide from the air. And that means taking the carbon dioxide out of the air into the soil where it will be stored. There's another technique which they're doing in Iceland, which is in Iceland, they've got lots of cheap geothermal energy that's from volcanoes and geysers and things like that. And
Mm.
they also have lots of basalt, which is the perfect stuff to store carbon dioxide. So what they're doing is they are taking carbon dioxide uh, from the air and then pumping it down into the basalt so that it will be absorbed by the basalt. This is a way of storing it. There's an idea to do that in places like Oman, where for a variety of geological reasons you have these dark colored rocks full of the right kind of silicates at the surface of the earth. And so you could pump carbon dioxide down into those and it would be geochemically trapped in the rocks.
Oh,
And
wow.
so, yeah, that's part of the idea.
That's
Um,
amazing. I
yeah,
actually heard of something similar, which was some volcanic rock. I think it might have been granite. They ground it up and enriched it, and then put it on farm fields. If they use it as fertilizer, I think, as well as it was picking up CO2. I can't remember if it was granite or not, but it was something very similar. It was really interesting.
Yeah, okay. It might well be the olivine type rocks.
Yeah. Well, uh, for carbon capture though, does it matter where you capture it? Because if you were to put all the carbon capture in one place, wouldn't that technically negatively affect the plant life and then hence the animal life?
Okay, well the one of the key ideas of carbon capture and storage is that you let's see you have a plant which is burning gas, okay, and it produces carbon dioxide. You trap the carbon dioxide and then you pump the carbon dioxide back down into through a pipeline back down into a underground reservoir, a natural underground reservoir. I mean, the gas that we use comes from giant underground reservoirs.
Mm.
So you drill down into it, you extract the gas, you then burn the gas to create electricity. What happens? Well, you're left with the carbon dioxide, which mostly goes into the atmosphere. And so the idea is you trap that CO2 and you just pump it back down into the reservoir from which it came. And the reservoirs are basically sandstones trapped under a clay layer, which prevents the gas from escaping. So by pumping the gas back down where it came from, or into a similar underground reservoir in the North Sea, then you've trapped it, and it can be trapped forever. The Norwegians currently do this in the North Sea. They have a field called the Sleipner Field
Hmm.
in the in the North Sea, just off the Norwegian coast, and there they get gas out of a natural gas reservoir, one of these sandstones,
Hmm.
and the gas is a mixture of natural carbon dioxide and methane, and they don't want the carbon dioxide. So on the rig, at the rig head, they split the carbon dioxide away from the methane, and then they pump the methane straight back down into this reservoir. So we know it can be done, and they've been doing it for years, and it's been shown to be very effective. So yes, this can all be done, but there's a cost implication. Obviously, somebody has to collect the CO2. Somebody then has to um, pump it down a pipeline to um, a gas wellhead, and then pump it down into a reservoir.
Mm.
So these are the sort of cost implications. It is done in places that the first one I saw was in Saskatchewan in Canada. It was what you call a pilot plant, but it was working very effectively. It was demonstrating how this could be done. And so what you then need to do is to ramp up the demonstration level to a full industrial plant. And so there are something like there are at least a dozen of these experimental things going on around the world.
Oh,
So
wow.
yeah,
How many would you need to reach if we were to say that first net zero wise, if we're trying to reach net zero and before it goes into the atmosphere, you're taking the CO2 from any processes, and then you were to give it to the plants. How many of those plants? I mean, you may not would process
um,
we need.
a very large number.
Guess
I don't
that.
have the actual number, but it would be a major industrial enterprise to actually reverse the carbon dioxide concentration in the atmosphere. We have been doing something similar with sulfur dioxide. You may have heard of acid rain,
Yeah.
okay, but I bet you haven't seen acid rain mentioned in the press lately.
No.
Yeah, and that's because about 10, 15 years ago, maybe slightly more, countries realized that the flue gases from the burning of coal containing sulfur produces sulfur dioxide, which is getting into the atmosphere, and then the sulfur dioxide was moving in the air from say Britain or
Hmm.
North America. It was going over um, Scandinavia, and as it mixed with the water vapor, it was becoming sulfuric acid. SO2 plus H2O gives you H2SO4, which is sulfuric acid, and the sulfuric acid was falling out with rain and killing off the Norwegian lakes. The Norwegians and the Swedes weren't very happy about that. And so the governments came to an agreement that wherever there was coal being burnt, we ought to put a sulfur scrubber on the factory chimney to take the sulfur dioxide out and then do whatever we needed to do with this solid sulfur dioxide, and that would clean the air, and so you wouldn't have acid rain anymore. And it worked really well. And basically, what we're talking about, the carbon dioxide, is doing something very similar. It just happens to be very much more expensive. And the other thing, of course, is when you're driving your car, or you're in a train or in an airplane,
Mm.
uh, there are many, many more point sources for carbon dioxide than there were point sources for sulfur dioxide. Sulfur dioxide, you just needed a factory chimney, okay?
Mm.
Limited number of point sources. But look at all the millions of cars there are on the road, and trucks and trains and buses and goodness knows what.
Mm.
It's dealing with point sources like that is the difficulty in bringing carbon dioxide levels down. If industry agreed tomorrow to limit the carbon dioxide coming out of coal burning, for example, in China or somewhere, or India or somewhere like that, okay, that would be a first step, but it wouldn't do much for carbon dioxide coming out of tailpipes. So one way around that is to say, well, okay, so we won't use gasoline and diesel in vehicles. Instead, we'll burn hydrogen as a fuel, because all you get when you burn hydrogen is oxygen and hydrogen as
Mm.
waste products, not CO2. And somebody has done that. You may have heard of JCB diggers and JCB bulldozers. JCB is the initials of JC Bamford, a British manufacturer of bulldozers and diggers and all that sort of thing. And so he challenged his engineers to actually make his vehicles run on hydrogen. And the engineers discovered that the principle is exactly the same. You have an internal combustion engine, which you use for petrol and diesel. And what happens there is you have a piston, which creates a space
Mm.
into which your gasoline goes, and then you use a spark to explode it, and that drives the piston. Okay, but it's the same with hydrogen. You put the hydrogen in the space, you add a spark, it goes bang, and the piston moves. And so he said, "Oh, that's amazing. I want that done on my vehicles." And so he had a fleet of vehicles running on hydrogen.
Did it
See?
work?
Yep. So it can be done, but the main problem is, where do you get your hydrogen from?
Yeah.
So currently, lots of companies are looking at how to create major stores of hydrogen as a potential fuel. Um, the thing about petrol and diesel, is that they're very high energy density. You've got a lot of energy in a tiny space. The
Mm.
thing about hydrogen is it's very similar. You've got a lot of energy in a tiny space. And so that's a good thing.
Mm.
So what we're currently doing, of course, is trying to move people away from petrol and diesel vehicles to electric vehicles.
Mm.
Um, but
Eventually, wouldn't you sort of over not a geological long time, but a human long time, wouldn't you sort of come to the opposite effect? Then you'd have lots of oxygen in the atmosphere and less CO2, and then if you were to go with hydrogen rather than petroleum, like
Yeah, that's a very interesting question, and I don't know that anybody's actually done the calculations to show how much oxygen there would be in the air from splitting off hydrogen. But that's a good question, and I don't know what the answer to that one would be.
it's interesting to consider there, I suppose. What was it? Ah, there was one other thing I wanted to ask about the carbon capture itself. Like, if you were to put a carbon capture plant, I don't know how it works, but if it's at a fixed location, um, to do the negative emission side of it, would it just automatically to balance? Would it just even itself out with the rest of the surrounding area? If you,
Yeah, I
I
see
said
what
that.
I see what you're saying. Well, if you imagine it the other way around, where is most CO2 going into the air? Most CO2 is going into the air in industrialized countries. So
Hmm.
In fact, if you measure the carbon dioxide, where we now measure the background carbon dioxide is in places like the South Pole and the top of the Mauna Loa volcano in Hawaii, because they're that's what we call background air, well away from industrial sources. But if you were to go to, say, the Ruhr Valley in Germany and measure the carbon dioxide in the air, you'd probably get figures up to about 500 parts per million because it's major industry source, lots of people live there, lots of vehicles, so the CO2 level goes up. So CO2 is unevenly spread around the world, but eventually the winds mix it all, so it's actually quite a well mixed gas. So the inverse, you're talking about the inverse. What would it be like if you put all your carbon capture um, fans, let's call them, in the UK? What sort of difference would that have? What sort of effect would it have? Well, it wouldn't do much for the CO2 levels in Germany if they weren't doing the same thing. So you really have to deploy these capture systems globally.
Hmm.
You can't just do it in one place.
Hmm. Okay. That makes sense. Um, what was I gonna ask? Oh yeah, there's this other thing that you said. I think it was polar amplification. Um, what exactly is that? I mean, I understand the words, but I don't understand why that happens.
Yeah, well, it's tied in with the refrigerator question.
Mhm.
Um, if you look at a globe with the temperatures on it, what you find is that whereas the global average temperature has increased by about 1.5 degrees, the temperature in the Arctic, for instance, has increased by at least 3 degrees. So it's increasing faster than the rest of the world. Uh, and because it's increasing faster, that means that ice is melting faster. Things are melting faster in the Arctic than further south. And so this is what we call polar amplification. It's the climate is getting a double whammy. It's getting warmer because of carbon dioxide going into the air, and it's getting warmer because the ice is melting. So you're losing the reflection of the solar energy. And so this is what's referred to as polar amplification of the global warming signal. Okay.
Okay. Actually, I remember I studied this once when I was doing my geography GCSE, but I can't remember. It had a different name. No, I can't remember it. It's something like cycle of something. It's
Yeah, well, there are lots of, there are lots
yeah.
of cycles. The carbon cycle, the nitrogen cycle, the hydrological cycle, and so on and so forth. All these cycles interact with one another in a complex way.
Oh, a difficult question, probably quite difficult, but what would you say is what would you suggest that would be the immediate actions for governments and industries to prioritize to combat climate change?
Yeah, okay. Well, I think the initially the most important action is to increase renewables at an increasingly rapid rate. That's increasing in particular wind and solar at an increasingly rapid rate. And also encouraging, and one way to do that is to do what our government is already proposing to do, which is to put more wind farms on these large offshore areas like the Dogger Bank. Okay, so they're already moving in the right direction. But equally, I think they need to make it much easier and by providing incentives, financial incentives for all house owners in the UK to have solar panels on their roofs. So, wind offshore, solar panels onshore. I don't, I'm not really a great fan of covering farm fields in solar panels, although, it
Resistance.
is, yeah, it is being done in some areas. I think it is, the word I would use is stupid to cover farm fields with solar panels and not cover roofs. I mean, why on earth not?
Yeah.
Um, you
That's-
could start by saying by incentivizing all local governments to cover all of the properties for which they're responsible with solar panels, and that's schools, office buildings, anything for which local governments are responsible, and that's quite a lot of buildings.
Mm.
Um,
Yeah.
Start by covering them with solar panels. Encourage all of local government to switch from petrol and diesel vehicles and petrol and diesel energy sources or gas sources to renewable energy, so that the sector over which government has direct control leads the way. Okay,
Mm.
what that would mean for a start is covering the Houses of Parliament with solar panels.
I wonder how that would look.
Yeah, well, it depends
Just
what color they are, doesn't it? I'll tell you
imagine
something interesting about solar panels. Right now, most of the solar panels we use are not as effective as they could be because they're mostly they are only using the energy. I think I'm correct in saying they're only using the energy in blue light,
oh,
and they need to they can increase. I forget. I'm not a physicist, so forgive me, but um, there is at least one other wavelength of light that they could be using, and uh, I forget the name of the well, it'll come to me probably, but there is a mineral that you can use in solar panels that will capture that additional um, light vibration.
oh wow. I think I've actually seen that as well. Apparently it makes it quite significantly more efficient, which is amazing.
Yes, yeah, but I think it increases it by about 30%.
Wow, amazing. Talking about technology then, what would you say are some of the most promising technologies available generally as well as for carbon capture and storage?
Okay, well,
By generally, I mean more
I'm a
re
great
like
yeah, I'm a
commercial.
great fan of electric vehicles. So I have a hybrid, um, and we need more of those. And the government has actually been very helpful by, encouraging the use of electric vehicles. And also, what they've done is across the country they've put in place a network of charging points. Now, the other thing about the whole electric vehicle story is that the batteries have been getting smaller and the charging has been getting very much faster. So now on a long trip, you can probably pull into a electric vehicle charging station on the M1.
Mm.
Just take one extra charge in less than 10 minutes that will get you all the way to Edinburgh.
Oh wow.
These are big steps forward. The other thing is that the batteries were thought to be too big and heavy to actually use in trucks, lorries. But we've obviously in the past few years it's been demonstrated that they work pretty well for buses. The thing about buses is that they, in effect, don't operate day and night round. Um,
Mm.
you just take your bus back to the bus station and charge it there. With trucks, it's more difficult because they don't have depots that they go to. They're on long haul. But now the battery sizes have come down to the extent where we should be soon seeing long haul trucks with which are electric vehicles. And
Oh,
the third thing is airplanes. Already there's an American company which is planning to have a fleet of small planes capable of 1,000-mile journeys. And the Norwegians are also working on the development of small planes, which will uh, go a fair way for European travel using
oh,
batteries. So these are big changes for the future. A lot of people who talk a lot about doom and gloom completely neglect these new technological developments.
mm,
They really don't have any idea what that the future is going to be very different.
mm. Wow. There about the airplane one, I think I saw somewhere that someone managed to make an airplane. Well, probably not one person, but yeah. But they filled it with solar panels everywhere on top, obviously, and it managed to do a whole flight just on the energy it created while flying, which was
Yeah, I mean
that's
that's been done in some of the, every now and then you have students do a race, like an electric vehicle race, or who can, or an electric plane race, and that sort of thing has been done at that level, but that's very much a sort of experimental level. Turning it
Yeah,
into a development project and then turning it beyond a development project into an industrial project where, everybody is now flying on this airplane that does 1,000 miles on a charge is the next big step.
yeah, yeah. It's also rather scary to think that it's being powered by solar panels while it's flying.
Well, it wouldn't be, yeah, well, of course, that was your example. My
Yeah,
example is it wouldn't be flying with solar panels, it would be flying with a battery.
sounds a bit safer.
Yeah.
Oh, dear. We actually went to the, I don't know if you probably heard of it, the Innovation Zero Congress a couple of weeks back. We went to it and saw lots of amazing technologies and ideas that could be implemented and would probably have a huge effect. But what would you say is the role of geology in all of this and finding new solutions to reaching net zero and negative emissions?
Yeah, well, I used to be a vice president in the Geological Society of London, and we began to get very interested in all of this, particularly, since geologists are the people that, find new resources, like, where are we going to get the lithium from for lithium ion batteries?
Mm.
And well, the second question is, will we need so much lithium if we can make smaller batteries that use less lithium? So all that sort of complication. But it's not just lithium, it's all sorts of metals are now needed for all the modern technologies that we have, in your mobile phone and in your computer. There are all sorts of strange elements like ytterbium and germanium and even gold that you wouldn't expect were there, and they have to be found. And geologists are obviously in the mining business,
Mm.
trying to find this stuff in large enough quantities so that it can be mined at a profit and provided to the industries that are making all these new products, and some of those metals will be needed in the batteries and all the other aspects of these novel technologies we'll need for the future.
Mm. Yeah. Uh, Like we actually had another talk a while back about the supply chain of lithium and whether it would work to get it from Cornwall rather than further away for
Yes, yeah,
significantly smaller amount in Cornwall than what is probably needed for UK.
that's possible. Yes, yeah.
Uh,
Ideally, with any mineral, you need to make it economic, you need a large amount.
yeah. Was lithium ever used in before, like before batteries and stuff? Was it ever used for anything? I mean, anything
Um,
significant?
Actually, in the medical sphere, they may still be using lithium to treat bipolar disorder, manic depression.
Oh well.
Yeah,
Yeah.
so it had medical uses.
Oh
I expect it was a lithium compound, but yeah,
wow.
I'm not sure. I'm not an expert on lithiums.
No, I was just wondering because I suppose if you could recycle it from something that's not being used at all, then that would be a nice source. That.
Now, you may or may not know this, but lithium in the periodic table, lithium is in the same family as sodium. And
Hmm.
it turns out that you can make sodium ion batteries instead of lithium ion batteries, and they are just not quite as effective.
Oh.
But we know there's a lot more sodium around than there is lithium because under the North Sea, under parts of the UK, under parts of Germany, there are enormous um, Permian salt deposits, which contain obviously loads of things like potassium and sodium and um, barium and what have you. So
Hmm.
sodium is not in short supply, and so it could be that one day somebody will make a sodium ion battery and use
Vicious enough.
use it for industrial purposes instead of a lithium ion battery.
I mean, that might help. It's. I suppose there are lots of these things that work for small things, but not
Mm.
as well for big ones. Yeah. Huh. Anyway, what would you say? I mean, how would you say that we could communicate better the urgency, let's say, of the climate change to the whole world and the public, that sort of thing?
Yeah, that's a very difficult question because climate scientists have been pounding the table and crying urgent, urgent for a very long time. Um, and it's been brought to the attention of politicians many times. In the US, Jim Hansen, who I mentioned earlier,
Mhm.
who at the time was director of the Goddard Institute for Space Science for NASA, he
Uh-huh.
gave a presentation to the US Congress in 1988, forecasting accurately that by the year 2000, um, we would really be clearly seeing signs of global warming, and he was spot on. So, people have known about this for a long time, but there is a reluctance. Um, Politicians, in my view, tend to be behind the ball when it comes to advances in knowledge. That's probably because a lot of them are the vast majority of politicians have almost zero science training. Most of them tend to be lawyers, and so they find science very difficult to get to grips with. They have scientific advisory panels, and of course, one of the first things you can do with a scientific advisory panel is ignore it if there's a cost implication. So, we have known for a long time about all this,
Mm.
and not a great deal has been done, but things are beginning. Like I said, with that graph of UK electricity production, it was when Boris Johnson got into power. One of the first things he asked for was a presentation from the UK Meteorological Office on global warming. And I
Oh,
think previously, when he was a journalist, he was anti-global warming. He thought it was a hoax or something like that. But after he had this presentation from the experts from the Met Office
mhm.
um, down in Exeter. Oh, Exeter, yeah, that's the university where Tim Lenton is at. Uh, he got on the case, and that helped to promote the development of wind farms across the UK.
Oh, well.
It can be done.
Yeah.
Yeah,
Everything can be done, I think, in
yeah.
theory.
I was at the UN Framework Convention on Climate Change meeting in 2009 in Copenhagen. I mean, these meetings get attended by something like 40, 50, 60,000 people,
Oh, wow.
and all with the same basic message. And
Mm.
even so, it's still extraordinarily difficult to get politicians to agree with what needs to be done. It wasn't until the 2015 meeting, which was in Paris, that the UN Framework Convention people agreed with that 1.5 to 2.0 with those what do you call them, boundaries for
Mm.
global warming.
Yeah.
That's quite recent.
Yeah, it's like I can't even remember what year it is. Oh, okay, found it.
Yeah.
Uh, no, I remember now what the question was that I forgot. You when you said about ice melting, and if we were to reach back to negative emissions to where we were, I think it was you said 1960 or something like that. Um, would ice come back to where it was then, or because I'm assuming that that ice built up over geological time.
Right, it's a very good question. And what we stumble into here is something called hysteresis, and it works as follows. First of all, you melt the ice, and so it begins to melt faster and faster and faster, and then it's all gone. Okay. To
Hmm.
make it grow back, you have to reduce the temperature by more than you warmed the ice in order to get it to grow back.
Hmm.
So if it was melting, if it started melting when your temperature was about 2 degrees and then it all went, you'd probably have to cool your temperature by 4 degrees to get it to start growing back.
Okay, so to mitigate what we messed up with the melting ice and the reflection and the attraction now from it. We'd actually have to go even further than we were in those times with the
Yes,
CO2.
yes. That's why I said in my book, I suggested, well, Jim Hansen suggests that we need to go back to 350 parts per million through these negative emissions.
Mhm.
But that 350 was what it was in, I don't know, about 1980.
Uh-huh.
Uh, my preference would be that we need to get it back to probably 300 parts per million, which is close to what it was in 1900, probably about what it was in 1920, somewhere about that. And that would help. But you know, that's my imagination. It's not a calculated thing.
Yeah, but it is still. It's sorry, just trying to think, understand it.
Okay, but there's another thing that you could do. Okay, um, one thing that people are working on. There's now a guy who used to be the UK's chief scientist, a fellow called Professor Sir David King. He's now at Cambridge, and he and his team are working on technologies to help us to solve this problem. And one of the things they're working on is the idea that you can have unmanned ships sailing the Arctic Ocean, taking sucking water up through the hull, and then spraying it out through funnels into the air to create cloud droplets, to cause clouds to form, low-level clouds, marine clouds, and these would have white tops, which then would reflect the solar energy. So that's I think that idea came up from, it might have come from a Professor Salter from University of Edinburgh. He's very much into these kinds of things. Anyway, it doesn't matter who thought it up. So that is one idea, and it has been suggested that not just for the Arctic, but some years ago when the idea first came about, it was that you could have these ships sailing across the Atlantic and the Pacific and the Indian Ocean. You would have a number of these ships pumping these water vapor up into the air, and what you need is little droplets, which would then become cloud condensation nuclei to cause clouds to form. But the white tops would reflect solar energy. And if you had them across all of the oceans, of course, you could do this in a global sense. But
Uh-huh.
if you really wanted to work on getting the Arctic ice to grow back to sea ice, then you might want to start focusing on the Arctic, on the
Mm.
Arctic Ocean.
Oh
So,
wow.
there are ideas to do these sort of things. I'm not sure that it's been costed, but
Mm.
it sort of sounds as if it ought to work in principle.
Yeah, well, it's really interesting as well. Lots of interesting technologies out there. And
Yeah.
something to develop.
One of the problems you need to think about is, okay, so we have this idea, great, it sounds good on paper. The question is, because it's a global problem and requires a global solution, who is going to pay for it?
Everyone.
Well, yeah, that's easy to say, but how do you get China and Russia and Indonesia and South Africa and Chile and the USA? How do you get them all to agree that they're going to actually pay for this?
Mm.
That's a trick. That's the difficulty with a lot of this global warming stuff. If you imagine all of these people sitting around the table in the meetings of the UN Framework Convention on Climate Change, they're all politicians from all of these countries with their environmental advisors, and uh, and Russia is thinking to itself, wait a minute, I'd rather like Siberia to become warmer so I could grow more wheat. And the Canadians are sitting next to them saying, yeah, man, that'd be great, wouldn't it? We extend the wheat growing north of Alberta and make more money. So not everybody is in agreement about, exactly what to do. In other words, we know there are going to be winners and losers. At the moment, the most noisy losers are the people who live on islands like atolls in the Pacific and Indian Ocean.
Mm.
And they're called, as a group, they're called the small island states. And they're not happy about being flooded out by sea level rise. But they are vociferous but very small minority. So you've got this game in which there are some very big players and some very small players who may have diametrically opposed rationales for how to get to grips with the problem.
Mm. Yeah, I mean, makes sense. I suppose there's upsides and downsides to everything, and it would be nice to have but all the upsides.
But that's why they call global warming a wicked problem.
Mm.
It's a transboundary problem, and getting people to agree on what to do about transboundary problems is not easy.
Can't imagine. Honestly, it would be horrible. Oh, I one thing that TAFU was trying to do is get into educational institutions and teaching young people about global warming and all that. Got quite a few projects on for that. I wanted to ask, what do you think you would say is the role of educational institutions and the media as well that play in shaping public perception and public action as well? So,
Well, the media is usually behind the ball, and up until very recently, the BBC had this problem because it's in addressing climate change, because its attitude was, oh, we must have balance, see. And so we'll get a climate scientist on to tell us all the bad news, and then we'll get a climate change denier to come on to tell us it's all bollocks. So, you know, that's part of the problem with the media is what game are they playing?
mm,
And that's a difficulty. With education, of course, then if you want the message to go into schools, the schools for the most part are run by local government. And so again, you are reliant on an agency, the local government agency who owns the schools, to be the arbiters of the message. Similarly, in the examination system, who's writing the exam papers, who's putting in questions about global warming.
mm,
Um, are the physics teachers as a bunch, are they all on board, or are they not? Why don't we have a consistent message through physics and chemistry and biology and geography of these major disciplines?
mm.
Are they connected, or they're still living in their different discipline silos, and there's not much messaging going on that way, because they haven't read the book.
Oh, yeah. When I was studying for my chemistry and biology and physics A levels, I also noticed there's lots of things that my physics teacher liked to connect things to the real world, which was really nice. It made it a lot more understandable. And he told me this thing about friction and how it worked. So I was really interested in that. And when it came to a question in the exam paper, I wrote it in. However, it was not in the mark scheme. And
Ah,
hence I got no marks for that question, even though in theory that's correct and it is more linking to the real world and it's similar with other things as well. That's one that stuck with me though.
yeah.
Uh,
I mean,
uh,
I do go into schools occasionally, even into junior schools, where the kids are about 8, 9, 10, and they're really interested to learn about this stuff. They're at that such a young age, their minds are still open.
yeah,
They haven't been corrupted by the scientific silo system.
yeah, yeah. There was actually, when was this? I don't remember. Someone said that there was this 6-year-old or 4-year-old or something who came up with this invention, obviously didn't make it, just came up with the idea. This chil young children can come up with lots of ideas, I think, just by giving them the problem, and they're like, why not do that?
Hmm.
Maybe not that one, but some of them are quite
Yeah.
interesting.
The expression is out of the mouths of babes and sucklings.
Oh dear. Um, Anyway, what was I gonna say next? Oh yeah. Um, what would be the impact if we trying to reach net zero by 2050? What would be the impact if we don't actually reach it then? Because we know you talked about what would be the impact if we did reach it and it would still be a negative impact.
Yeah.
If we even didn't reach it, what would be the impact of that?
Yeah, okay. So if we don't manage to get to net zero, but we have sort of increasing amounts of carbon dioxide in the atmosphere and other greenhouse gases,
Mm,
then water vapor will also go up. So it's another greenhouse gas. And so our temperatures will get progressively warmer in proportion to the amount of burning of fossil fuel that's going on.
mm,
And this will push us more towards the same conditions that geologists tell us that the planet experienced in previous very warm times. You know, the planet has oscillated through what we call greenhouse phases when the temperatures were very warm and icehouse phases when it was rather cold, uh,
mm,
like the ice age we were recently living in. And we think we understand why that is. And it looks very much as though we are currently breaking the mold and moving quite sharply in a direction that's going to take us back to one of these sort of warm time equivalents,
mm,
analogs of the past. Um, and that could last for a very long time because we know that the rate at which carbon dioxide is taken out of the atmosphere is actually, by nature, is actually very slow. So if we weren't using some technology to take it, then the carbon dioxide in the atmosphere, you'd get an initial reduction down to say, a certain level, and then it could take 10,000 years to get it down to back to what it was yesterday. So we're talking about very long geological timescales. And the reason is that carbon dioxide in the atmosphere is in equilibrium with carbon dioxide in the ocean. The CO2 is exchanged across the air-water interface, and the gas has to be in equilibrium across that. So if you increase carbon dioxide in the air, you increase the carbon dioxide in the ocean. Eventually, you get to a point where the ocean becomes unable to take in a lot more carbon dioxide, and in order to keep the equilibrium, the air has to take more of the carbon dioxide. So the amount in the carbon dioxide in the air goes up.
mhm.
So similarly, if you try to take carbon dioxide out of the air, because you are changing the equilibrium, you don't you have to actually take out more carbon dioxide than you thought you would have needed in order to achieve the same result, because you have to maintain that equilibrium
Yeah.
across the air-water interface. So it does take a long time.
Mm,
Uh, the ocean actually contains a huge amount of carbon dioxide. The deep ocean contains something like 38,000 gigatons of carbon dioxide. So it's an enormous amount of carbon dioxide stuck down in the deep ocean. And it's unlikely it's going to come out anytime soon, but um,
mm.
that helps. That's the sort of big stabilizing factor that prevents us going to one extreme or another extreme suddenly.
Oh, yeah, wow. I also looked into what's it called? Seaweed and kelp that also think they said nearly as much as dense forests with high biodiversity. It absorbs nearly as much, which is also really amazing. And not
Yeah,
many people think about it.
yeah. Well, marine plants are just, they're just like trees. They eat carbon dioxide
Yeah.
to grow. So kelp, you can think of kelp as a tree underwater. It's using carbon dioxide to grow itself. And so similarly, the phytoplankton are otherwise known as the grass of the sea. Basically, they grow out of water by absorbing the carbon dioxide.
Hmm.
So if you will, the phytoplankton are the grass and the kelp are the trees, and they are doing the same as the biology on land, trees and grasses.
Yeah, it's just you don't often think about it as much, which is kind of interesting, really. Why?
Yeah. Well, as an oceanographer, one of the reasons I got into oceanography was because we knew so little about the ocean, and I wanted to find out what was going on down there. And that stimulates. There's been a big growth in oceanography over the since the Second World War.
Oh.
A lot of it's stimulated by the development of new technologies for anti-submarine warfare that developed in the Second World War. So, you do tend to get these spin-offs from war where money goes into developing new technologies. And then when the war's finished, you find you suddenly got a new technology you can use for something that has nothing to do with war, but gives you more scientific information.
That's quite fun, actually. Well, in quotation marks, it'll ask the part anyway.
Well,
Wow.
think of rocketry. I mean, the one of the the developers of rocketry was Nazi Germany, and when the US took over Nazi Germany, in effect, they captured the Werner von Braun, who was the guy who invented the V2 rocket, which bombarded Britain during the Second World War, and he was behind NASA's development of rocketry.
Oh,
Now, now they are using it mostly for peaceful purposes.
oh dear. Oh. Do you do you find that do you find that there is movement happening in the right direction, or enough movement happening at a fast enough increase rate and in the right direction? And does that demotivate you at all?
Well, I have some colleagues who sort of, tear out their hair in desperation because politicians aren't doing things quickly enough. But on the other hand, then I read Hannah Ritchie's book, and what she demonstrates is that there is a lot going on that many people just don't know about because they haven't got the statistics at their fingertips like she does. So I recommend that everybody should buy a copy of Hannah Ritchie's book, Not the End of the World, because it is so informative about the technologies we have, how they are changing things. I mean, the major change that is really obvious, should be really obvious to everybody, is that the cost of the basic cost of solar energy in 1970 was something like well over $100 per kilowatt or whatever it was, whatever electrical measurement you want.
Mm.
And by now it's down to just a few cents. So it's cheaper. So wind and solar energy are now cheaper to and producing electricity than burning gas or oil or coal. Okay, so we should be using them more and more and more, and they will get cheaper and cheaper and cheaper. And someday maybe we'll have clothing that's solar paneled, and we'll
That'd be
on our
interesting.
windows. You've heard about thin film technology. These thin film technology is you get thin film of something that is so thin you can stick it on your window, and you wouldn't even know it's there. But within it, it's got the potential uh, for creating energy from the sun. Okay,
Wow,
yeah, and
amazing.
that would pump energy into your house. You'd be using that as one of your electricity sources. Right now, if you put solar panels on your roof, if you have a house, you can actually be generating so much electricity, you can be putting electricity back into the grid
Mm.
instead of paying for it to come through the grid. So, these changes are already happening. It's right here, right now.
Yeah, yeah, which
It's just
is really
not enough.
important to remember.
Hmm.
Yeah. Another thing that we focus on quite a lot is inter-industry. Sorry, that was really hard to say. Um, collaboration and solution finding. How important have you found that to be, and how important do you think it is?
Well, I mean, I think Bill Gates's book addresses that because he's displaying the whole panoply of technologies that could be used right now, and as well he's exploring where the breakthroughs are needed. There's another very useful book too, which you can buy in Waterstones. It's called Drawdown, and there's a Drawdown website as well. And I think the Drawdown team, I think lists 100 different technologies that we now have and can use and should be using to actually bring down carbon dioxide. Uh,
Mm,
so what we need is the the agency that it would be most effective at bringing all the industries together is government. But in the years starting in 1980, Ronald Reagan became president of the United States, and Margaret Thatcher was prime minister of the UK, and the two of them agreed on deregulation. And deregulation was very important. For Ronald Reagan, government was the problem, not the message.
mm,
And so the two of them actually helped to send our industry offshore to China because it was deregulated. You could take your manufacturing out of the UK, send it to China, get everything made more cheaply. That's why China is really coming up because we sent our manufacturing industry there. Everybody sent their manufacturing industry to China. So governments can really get in the way of us successfully tackling the problem if they come up with the wrong ideas. Let me give you another example. Not long ago, this government and governments in other places too, decided that it would be much better for the planet if we burnt diesel rather than petrol. Unfortunately, what they've now discovered is that by burning diesel, you fill the air with these micro 2.5 micron little particles that get into people's lungs and kill children, through asthma. So, governments can do the wrong thing, probably for all the right reasons. But anyway, they're now reversing their position on that. On that. So yeah, getting industries to work together is not all that easy because an individual industry is a profit-making center,
mm.
right? Now, what you're asking for is for several profit-making centers to sort of band together. They really don't like to do that.
Asking for everyone to take personal responsibility.
Yes, well, taking personal responsibility is not the same as taking corporate responsibility.
Well,
With
if
corporate responsibility, you are responsible to your shareholders, not to the planet.
technically you're also responsible to your stakeholders. Planet is a stakeholder.
Ah, yeah, yeah. Where does it say that in the shareholder manifest?
Oh dear.
You and I might agree on that, but the corporate CEO might not.
Oh dear. True. And yeah, three more things I want to ask you about. One is what can everyone do? What, in your view, is things that everyone can do to reduce emissions, fight climate change, and protect the local environment as well? What would you say? I know you
Yeah,
mentioned
well,
some of the things on your slide, but like
I
maybe.
did. Yeah, yeah. Well, it depends. If you own a house, then there are things you can do with your house. Solar panels, you can get a heat pump, you can change your gas boiler for a heat pump, you can do various things, insulate, add solar panels, blah, blah, blah.
Yeah.
You can eat less meat. Actually, not all meats are as bad as others. Cattle produce something like 10 times as much carbon in the form of carbon dioxide or methane than, say, pigs. Lamb and beef are the two main animal sources of greenhouse gases from the agriculture industry. Chickens, much less so. So by changing your diet and eating less beef and more chicken, I mean, that's one way to go. If you wanted to, say, I'm going to do something for the planet. You can also eat more vegetables. You could say, well, I'm not going to eat so much meat this week. I'm going to eat maybe 3 meals with meat in, and the rest are going to be vegetables. And you can get lots of protein out of vegetables, beans, for example. So, there are things that you can do just with your lifestyle like that. You can obviously decide that if you can afford a car, to get an electric car. That's pretty expensive, or a hybrid. Um, you can you can try and work with your local community to get more buses converted to battery, so they
Mm.
become electric. Lots of the buses in London are now electric. I used to live in Guildford, and some of the buses there went electric, but not most of them.
Mm.
What else can you do? There's a lot of don't fly so much. You really need to fly on holiday. Um, these are decisions, they're lifestyle decisions, some of them. I mean, I don't think it's a lifestyle decision to put solar panels on your roof, get a heat pump, or put um, better insulation in your roof. I don't, that's not a lifestyle decision. That's just common sense. Um, Buying a hybrid instead of a
Factor
petrol car
is
is
money.
not that's not lifestyle either. But choosing whether to change what you eat or choosing not to fly as much, those are more tied into what you might call lifestyle decisions.
Yeah.
And people have to make their minds up, what they want to do.
Mm. Yeah, definitely. Um, One other thing, we bought you a book yesterday actually. It's arriving I think tomorrow or something like that. And we can't wait to read it because now the academic year is over. Have a bit of time. Um, could you maybe give us a little bit of preview of what you discussed in the book?
Okay, well, um, the icy planet is about this whole question of what the role of ice is on the planet, how ice is working to, either give us a refrigerator or melting away to give us water in the ocean. So it's global warming with a focus on ice
Mm,
in the high mountains and the two polar regions. One of the things about high mountains is that a lot of them occur in places where, like in the Himalayas, where people are actually very dependent on the water supply from the melting of the ice in the mountains. And so, if you were to seriously reduce the amount of snow and ice in the Himalayas, it would have tremendous knock-on effects downstream for all the farmers and anybody who drinks or uses water downstream in the whole of the Indian subcontinent, which includes Pakistan and any other areas like Afghanistan, that really depend on the water supply from the mountains.
uh,
And I don't believe that that has been taken into consideration enough. So, water supply is a very important knock-on thing from global warming. With winners and losers, the Intergovernmental Panel on Climate Change has done this climate modeling to show that some areas would, with warming by the end of the century, some areas would get much drier, some areas would get much wetter. The areas that would get much drier are the ones that are already dry, like Chile, Mexico, Africa, much of Africa, the whole of the Mediterranean basin, including all of Spain, Portugal, Italy, and Greece,
yeah.
and then India and Pakistan and Afghanistan and large parts of China as well. So they would have increasingly arid conditions, which is again gets back to thinking about their water supply and how much they would have. And then the other side of the coin is that the areas that are now tend to be wet would get increasingly wetter because there'd be more water vapor in the air, and more water vapor means more rain. So right now in the UK, we tend to be drier in the southeast and wetter in, say, Scotland,
Mm,
and that's just going to get more extreme. So the southern UK is going to get progressively drier, but not as arid as the Mediterranean is going to get, and Scotland is going to get quite significantly wetter, as is North Germany, Scandinavia, Canada, and other areas like that. So you can see you can anticipate these potential changes, and it's just sort of common sense, really.
yeah. It's interesting to see it all laid out all together, which I can't wait to read it.
Yeah,
Uh,
well, what I do in the book is I take a tour through all the different regions to say, okay, here's Antarctica. What's happening in Antarctica? Is it serious? If it's serious, is it serious everywhere in Antarctica, or is it just a few places in Antarctica? Then I go to the Arctic. A lot more problems in the Arctic because, as I said earlier, the Arctic is a lot warmer than Antarctica in the first place. And then I go to the high mountains. So I explore these different regions, and then I look at the impact on sea level
mhm.
because sea level is a global consequence. That's what people tend to forget. You know, they realize they can think about their own individual country, but what they forget is that much of the climate is decided by the ocean, which is kind of global. 72% or 71% of the Earth is covered by the ocean. And so we really need to pay attention to what's going on in the ocean because A, it's a source of water for rainfall and snowfall. And B, you know, if it goes up, if the level goes up, which it already is, then every country around the world is going to be experiencing it, and some will have much more than others. Funny enough, one of the places that will have the highest sea level rise is the east coast of the United States, and I doubt very much that there are many politicians in Congress who realize that, or if they do realize it, we're probably in denial about it.
Uh, but that really does sound super interesting. I can't wait. One other thing we're super excited about is your upcoming lecture at the University of Bedfordshire. Could you maybe give us a small preview of what we can expect to learn?
Yeah, well, I probably would give an expansion on that to a sort of 50 minutes or so on this lecture,
Mhm.
um, because I have a more complex lecture that has all these other different aspects that you and I have touched on are actually mentioned in the lecture, like winners and losers and hydrogen economy and all those other sorts of things, which there was no room in this particular talk to do all that. So it's going to be an extended look at uh, climate change, climate change and technology and economics and where it's all leading,
Mm.
and what about the future and where is our future going if we keep on doing this stuff?
Mm. Yeah, sounds super interesting. Can't wait. And thank you again for doing it.
You're welcome.
Lastly, is there anything else you would like to say to our audience, any message you'd like to give everyone?
Well, I'm assuming most of our audience is young, like you. Is that right?
Yeah, mostly.
Okay. Well, you know, I mean, I'm 82. How old are you?
16.
16. Okay. Well, you know, that's that's a fair gap between us. So I grew up in a climate which is much cooler than you. You're now growing up in a climate which is much warmer than I've experienced, except till I got into my 60s and 70s.
Mm,
So you can expect the same sort of profile, you know, that just as I went from a sort of coolish climate to one that's quite warm, you're going to go one which is this degree of warmth to one which is quite significantly warmer. And it's going to have some worrisome effects. One thing we haven't talked about is the effect on biology.
yeah.
How are these changes? How is increased CO2 in the air and increased warming and changes in rainfall? How is that going to impact the crops that we rely on? And I've seen it read that I mean I know that there have been greenhouse experiments where Dutch guys have pumped lots of CO2 into greenhouses growing tomatoes, and the tomatoes have gone wild. They've gone crazy, you know, lots of tomatoes. But the trouble is that tomatoes are not every plant, and some plants actually don't appreciate increased carbon dioxide, and other plants don't appreciate increased heat. And so I don't think anybody has yet done had a comprehensive look at what all the biota would be like in the future if say our climate warmed by an average of 3 degrees, which means 6 to 8 degrees in the polar regions. what would that do to our all the biology on which we depend? You know,
Mm.
uh, the atmosphere and the climate and the ecosystem. This is our support system, and right now we're interfering with our support system. Is this wise? Well, probably not. Uh, but what can we say about what's likely? And the Intergovernmental Panel on Climate Change, which produces a report every 5 years or so, has these forward looks where they look at, what will be the effect on coral reefs?
Mm.
Um, will there be, what they expect is there will be lots more coral bleaching. When coral bleaching happens, the coral skeleton stays there, but the little creatures that live inside it and make it colored disappear.
Mm.
Um, and the important thing about coral reefs is that they are the nurseries for ocean fish. So if you're killing off your coral reef, you're also potentially killing off the nursery for a lot of ocean fish. So, these are sort of all these little knock-on effects that people aren't taking into consideration.
Yeah, and that will eventually lead to us as well.
Yes, and now there's another one. I just read this in a press release from the Alfred Wegener Institute in Kiel in Germany, in Bremerhaven in Germany. And they've been doing this study of what will happen to the Arctic as it continues to warm. And one possibility is that it may turn into a large jellyfish lake. Now, before you think that's too far-fetched, the Black the Black Sea has already turned into a large jellyfish lake. So
Mhm.
whereas it used to be quite productive of fish and so on, it's now its only product is jellyfish. So there are problems. One of which is that when we put fertilizer on fields and it rains, the fertilizer runs off, gets into the rivers, gets down to the river mouth, like they say the Gulf of Mississippi off the Mississippi Delta. Okay, and you pour all these nutrients into the ocean, and the algae go crazy. Wow, food, food, So they eat all this stuff up, and then they die. And when they die, they decompose, and the decomposition takes the oxygen out of the ocean. And so
Mm.
you're left with no oxygen for the fish. So you have what's called an oceanic dead zone. And some of these are really large. Most of the Baltic Sea is now an oceanic dead zone. Most of the uh, eastern Gulf of Mexico off the Mississippi Delta is now an ecological dead zone because of these things. This
Mm.
is not directly related to climate. This is humanity's effect on different parts of the planet. And so when you combine that with the fact that the ocean is getting progressively hotter, and you also have these dead zones, uh, you know, we're faced with this sort of a significant challenge as to how we manage the ocean, which is where an awful lot of people's food comes from.
Yeah. Uh, I suppose there's even any purely biological problem, in quotation marks, it will have some effect on the atmosphere and its ecosystem, and that effect will then affect the atmosphere and climate change, and in turn us. So it's important to consider everything. Everything is important.
This interconnections are everywhere, and that's what I'm going to hold it up again. That's what that's all about: is the interconnections between all the discipline silos. We ought to stop thinking in discipline silos and start to think about the interconnectedness of everything. It's really important.
Yeah, definitely. Well, it was a huge privilege to have you with us today, Dr. Summerhayes. Thank you very much. Your insights into climate change and your dedication to fighting climate change and doing action are really inspiring. Thank you.
You're very welcome.
Your work insights on the critical state of our planet and it really guides us towards solutions for a sustainable future. And on behalf of our audience and everyone listening, thank you again for sharing all your expertise and unwavering commitment to the crucial cause. Um, we really eagerly anticipate your upcoming lecture at the University of Bedfordshire, and thank you again for your time and invaluable contributions here and then. And thank you all for joining us, and I'm sure you all would all agree that we have learned a lot from Dr. Summerhayes, and it is on us now to use what we've learned and apply it to incorporate it, into our daily lives. And don't forget to be responsible, guys. See you soon. Bye.
Well said. Bye bye.